information that doesn't even tell us about that. It's all about what's happening now. We realize humans adapted to climate changes, and they always will. That's why we're here and other people aren't. And I'm on the other side. Don't say that global warming is causing all of our problems.
No, I wouldn't say it was causing all of
I know you're not, but I'm on the other side that, that let's tell the whole story.
Yeah, no, so the whole story would be that, in fact, we had much higher CO2 concentrations 700, 800 million years ago. We peaked, well, actually not higher than now, not at that time frame. Earlier than that, in geologic history we have, prior to the evolution of a lot of plants and animals that exist today. And we have had higher temperatures even within the last 11,000 years. What we have not had is anything that, so right now, what's interesting in that science paper that came out yesterday, in the Holocene, the last 11,000 years since we are actually in a period where we should be cool. The beginning of the 19th century was us entering an interglacial cool period. Instead of that, we are at the warmest period in the last 11,000 years, and at a rate of change that's unprecedented. Even if we go back in those Vostok ice cores, we can go back now almost 750 million years to look at CO2 and temperature. And the cycles go up, the cycles go down. Where we are now in CO2, though, is a peak that's equivalent to what we've seen in all these other interglacial cycles. And if you plot on top of that where current CO2 concentrations are, they're completely off the scale. And so that's the point. It's not that things haven't changed in the past. They haven't changed at this rate. So we're entering new territory. And nobody would claim that's our only or maybe even our biggest problem, but it's got the potential to significantly change the distribution of plants and animals and the climate on the planet. And so, that may be good or bad for certain areas, but my take on that would be it's going to be different, and I don't think we know enough about how different it's going to be to say whether it's good or bad.
Excellent.
I'm not going to mess around with this. I do want to talk just briefly. I'm only going to mention the troposphere and stratosphere for a minute. So this is the structure of the atmosphere. If we're thinking about the surface of the planet and going up. So if you go up in elevation in an airplane or going up a mountain, what happens to temperature? It gets colder, right? The further you go away, the higher you go, the colder it gets. Okay, that's what we're used to. And that's what's shown here. And so the troposphere is the part of the atmosphere nearest the planet. And it does get colder as you go higher. That's really important for rain. Then something really interesting happens. Above the troposphere, when you get into the stratosphere, the higher you go, the hotter it gets. It's exactly the opposite. So the stratosphere is this layer above the troposphere, and the reason it's important is it's the layer that has ozone concentrations that intercept ultraviolet radiation and prevent it from reaching the planet. So in the troposphere, temperature decreases with altitude. Now I'll show you in a minute. It's pretty predictable. The average, globally, the average environment, they call that the environmental lapse rate, the rate of temperature drop as you go up. And it's 6.5 degrees Celsius, centigrade, per kilometer, per 1,000 meters. That would be roughly 12 degrees for every 0.6 miles. Okay, so somewhere in that ballpark. Say roughly 24 degrees a mile or something at Fahrenheit. So if it's 76 degrees, by the time you go up 3 miles, it's freezing. Okay? It's cold. It's 0 degrees. In the stratosphere, it's exactly the opposite. It's warmer as you go up, and the reason is that ozone absorbs ultraviolet radiation. So just like the gases down here absorb infrared when it's going out, ozone absorbs ultraviolet when it's coming in. And what that does is it's good because ultraviolet is very damaging to tissues. Okay, so we don't want a lot of it on the surface of the planet. But it also keeps the top of the stratosphere warmer. So think about it this way. What does warm air do? Does warm air rises, right? So in the troposphere, if the surface is getting warmed, it's going to rise. And it's going to keep this troposphere mixed up all the time because cold air is on the top, warm air is on the bottom, warm air is less dense, so warm air is rising, cold air is falling. The troposphere is very well mixed globally. The stratosphere is very stable because it's cold on the bottom and warm on the top. It's stratified, and it doesn't mix very much. There's another story associated with that about things that get into the stratosphere and how long they stay there. They stay there a long time. That's part of the problem with things like chlorofluorocarbons. Once they get into the stratosphere, they don't mix out very quickly, and so that's why that has to do with ozone depletion, which is another problem. Okay, but this mixing of the troposphere is going to be really important because that's part of our weather patterns. So, let's see, I'm going to just, we already talked about Earth as a heat engine, so that's what I want to pick up on right away. We think about the Earth, so one thing is the Earth's tilted. We spin around, we orbit around the sun, but we're on an axis that's tilted right now 23.5 degrees off 90 degrees, and so we're on a tilted axis. The hot spot on the planet is going to be, think about the sun being over here. It's very large, so we can think about this, the rays of the sun pretty much being parallel coming into the Earth. Where's the hot spot on the planet? The hot spot is going to be the part that's perpendicular to the sun's rays. Okay. So that's not always the equator because we're tilted, but it's whatever part of the planet is perpendicular to the sun. That's what's going to get heated up the most. And the reason is that the sun's rays right there are the most concentrated. Whoops, sorry. They're the most concentrated here. As you go towards the poles, that sunlight is spread over a larger area. Okay? And it also has to go through a longer part of the atmosphere. This is the shortest path through the atmosphere. This is longer. So the planet gets hot at wherever the sun's directly overhead, and it's cool towards the poles. And that sets up global circulation patterns. Oh, and this is okay, more detail than we need here. But what I'll tell you is, so hot air rises, we know that, right? And we know that when you go up, it gets cooler. So if air starts at the planet and it's rising, it's going to cool. If it's got water vapor in it, what's going to happen to that water vapor as it cools?
Yes.
Exactly. And if there's cloud condensation nuclei are going to form raindrops, it's going to rain locally. So rising air, cooling air, condensation of water is what's going to lead to rain locally. The exact opposite happens if air falls. If air falls, it actually becomes compressed as it comes down toward, because of greater pressure, air pressure. So falling air mass becomes compressed and it actually heats up. That process is called adiabatic heating. Okay? And that warmer air is actually drier than it was when it started because it can hold more water vapor than when it started. So you end up with this air, air expands when it rises, it cools off, that's why it rains. When air masses are falling, they actually compress and heat up, and they can absorb more water vapor from the area where they're falling. We don't have to worry about the rate of that temperature change. What happens here? So this is, let's just imagine we're at a point where the sun is directly overhead at the equator. That's the hot spot on the planet. So we're heating up the planet and air is rising. As air rises, it cools. Water condenses, rain falls. So what that does is it sets up two big circulation cells on either side of the hot spot. In this case, the equator. We call the zone where these two, so what happens, let's say, explain it this way. We have rising air that rises up to the top of the troposphere. When it hits the layer between the troposphere and the stratosphere, that tropopause, it gets forced north and south. Okay, because the stratosphere is the stable layer up above it. So we have rising air that rises and then gets forced north and south, and it goes about 30 degrees north and south until it falls back down to the surface of the planet. Where that air is rising, that's called the intertropical convergence zone. It's sometimes abbreviated ITCZ, and it's where those two big circulation cells come together, and that's the wettest part of the planet. It rains there all the time. It rains year-round. So in fact, if you look at the Weather Channel or some weather maps, and you see a pattern that looks like this around the tropics, that band of cloud formation, that's the intertropical convergence zone. That's where those two cells are coming together. That's where you have rising air, cloud formation, a lot of water condensation. Okay, so that's why it's wet at the tropics. Then what happens when this air is falling? It's heating up. It's already lost all of its water. Now it's dropping down to the planet and it's heating up. That's where we ought to expect some of the world's major deserts. Okay? Those are about 30 degrees north and south are permanent high pressure areas. And in fact, that's where most of the world's hot deserts are. And then to complete this, we have polar circulation cells. So any place that the air rises, that's low pressure, high rainfall. Any place that falls is high pressure, low rainfall. So we end up with temperate forests at around 60 degrees north and south, where it's wetter again. And then in the poles, you end up with basically polar deserts. Okay, so that global circulation pattern actually explains a lot about the distribution of different climate bands on the planet. Then it gets a little more complicated because the Earth is spinning, so those north and south flow of air gets deflected. That's called the Coriolis force. And in the northern hemisphere, air is always deflected to the right of the direction of movement. In the southern hemisphere, it's always to the left. So that sets up the trade winds and the westerlies and the easterlies. And I won't spend a lot of time on this. I just want to make the point that this is basically, put this all together, those are the circulation patterns in the atmosphere that explain global climate on a big scale. Okay? So there's the reason that we have the wetter tropics, we have the drier 30 degrees north and south, we have wetter forests at 60 degrees north and south, and then we have dry conditions at the poles again. Those are the names of those circulation cells. I don't care that you know them. They're all named, well, Farrell and Hadley are named after the scientists that discovered them. Polar is obviously polar. But for now, if we look at the planet, here's the distribution of the wettest and driest areas on the planet. Well, the wettest areas are at the tropics, the intertropical convergence zone, and then we get kind of wetter areas again at 60 degrees north and south. The driest areas are about 30 degrees north and south. Things are, now, if it was a bowling ball or a billiard ball, it would be distributed just like those idealized circulation cells that I showed you. But because the amount of land mass and oceans are unevenly distributed and we have mountains, it breaks up those flow patterns. And that's one of the reasons why we have climate bands that are oriented north-south in the United States, is because the Rocky Mountains and the Sierra Nevadas break up that pattern. But otherwise, it would be banded a lot like we see in Africa and Europe. So that's the weather patterns. This is the distribution of the Earth's major biomes. Rainforests, deserts, temperate forests, grasslands. And if you flip back and forth between these two, there's a lot of congruence in those patterns. And climate patterns do determine the distribution of the major biomes around the planet. And this is a map of the major soil types in the world. And it also reflects the same patterns. So again, that's why I tell my ecology class, climate is a really important environmental driver. It influences the distribution of soils and biotypes around the world. We can probably skip a lot of this, but just to make the point that seasonality, the reason that we have 4 seasons here, the reason that we have, so in the tropics, the intertropical convergence zone is not always at 0 degrees. Because the Earth is tilted 23.5 degrees, some parts of the year that intertropical convergence zone is at 23.5 degrees north. Other parts of the year it's at 23.5 degrees south. That's what defines the tropics, how far that hot spot goes up and down on an annual cycle. So another way of looking at it, we look at this. At the equinox, the autumn and spring equinoxes, the hot spot, the intertropical convergence zone, is directly on the equator. But in our northern hemisphere summer, it's at 23.5 degrees north.